All right, so a couple of things I want to mention before we get going. So yeah, I mentioned it in class on Friday. Yes, there's just a reminder. That Connect assignment I pushed up a couple days. So the Excel assignment is due at the end of the day today. But if you want to, have some more of that Connect assignment to work on, that'll be due at the end of the day Wednesday. Okay. Also, we have a Learn Smart assignment, that Chapter 4 Learn Smart, that you need to do before we start class on Wednesday. Okay. So that due date isn't the end of the day, it's before we start class on Wednesday. It should take 10 minutes, kind of go through it. We'll start talking about probability today, but that'll get us kind of warmed up. I'll also be putting up a video to watch before Wednesday. I won't ask kind of specific eye clickers on it. It'll be something that we'll probably touch on today. We'll kind of set us up for Wednesday if you do have time to want to watch, but I realize you have a lot of other things going on. So I'm not going to kind of expect you watch that, but it'll be an additional video that kind of goes over some stuff we'll talk about today and Wednesday. So you can kind of go back to that as we get closer to the exam. It's kind of an additional resource. So you might see that pop up there, but don't think you have to watch that before Wednesday. Just to give time. I also, on number 14 on this Connect assignment, something's going wrong with kind of on their end. It's not taking the correct answer. And the issue, which I guess I should be telling them, but also you, is it's a good kind of it's a good time to point this out. When you're in Excel, and I'll show you here in a second, you can change the format of different variables. And I'm sure that's what they did when they calculated. So if I see 0.25, that's what I put into a cell in Excel. I can change the format so that it shows up as 25%. There's like a built-in kind of thing that Excel recognizes, okay, even though this is 0.25, if we want to show the percentage, it can convert it by multiplying by 140, right? So actually, whatever you end up with that correlation coefficient for number 14 on the Connect, it actually is off by 2 decimals, right? So it's close, but it's off by some decimals. And that's because I'm guessing on their end, they just had it formatted as a percent. So I'll show that to you real quick here. And I try to stay away from this in any assignment or any example I've given you. But since, there's an issue with that Connect, I think it's at least worth kind of looking at. So let's go. So make sure everyone see this. So if I put 0.25 in a cell here, I can click on that cell and go up here and under home, there's all these different formatting options. I can put a dollar, change it to accounting format, put the $sign in front of it. There's a percentage one, but all that does is it changes how it's shown to you. It's still stored in Excel as 0.25. Right? You wouldn't think this plays too much of a role when you start calculating things like variance. Because we're squaring things, you shouldn't just be moving the decimal 2 places, you should be moving it 4. And so just to not worry about all that, we always deal with the variables kind of in that probability format or the proportion format. So you should never be kind of using these format buttons for anything we're doing. It doesn't really change the value. It just displays differently. The problem is when you see that, you think, oh, 25 is the value stored in that cell, when in fact, the value behind it actually is 0.25. So we'll go back, kind of this comma is kind of our normal probability format. And that's why there's an issue with that one. Their end, they give you an Excel file and it's in the numbers, but I'm guessing the original one they had was probably stored like that. And that's why their answer's off. Okay. Any questions for me before we kind of dive into the material today? I think that's kind of all the kind of housekeeping stuff. Also for the couple icons at the end of the week, I'll get those uploaded this afternoon, so I'll get all of those up there in this course. No questions? So, we're gonna start. We went through descriptive statistics. We're gonna start on kind of the next chapter, next subject, which is probability. So we'll go over some of the basics today. That Learn Smart has kind of like the next level, a little bit more complicated. So that'll kind of take you through, get us ready for the stuff a little bit harder. But today we'll kind of focus on some basic notation and kind of see where we're going. So probability, we think about what we're talking about. Generally, it's like, I think it's like, intuitive, when we hear phrases like, what are the chances that this thing changes? What's the odds, right, that this investment becomes profitable? What's the likelihood? All those are terms basically for, look, we don't know what's going to happen, right? We know there's a bunch of different outcomes. When I, increase prices, potentially I see that, sales increases, decreases, or stays the same, right? I can see different outcomes, but I know that if prices go up, it's more likely I would see sales increase. I know some of the outcomes are more likely to occur than others, right? But I still don't know what the outcome is going to be. So, if I've got this variety of outcomes, I might be interested in which one's the most likely, which one's the least likely, right? Because I'm making plans for the future. I'm trying to project things for the future. I need to incorporate that. Right? So we're going to set this up and call these things that have unexpected or unknown outcomes experiments. Right? So experiment basically is anything where we don't know what the outcome is going to be, but we then, through running this experiment, are able to then observe the outcomes. This could be as simple as I've got a dice, I roll it, I know I can get 1 through 6. I don't know which one's going to come up, but I can roll that dice and then record what number I see. Right? So simple as rolling a dice could be our experiment. We've got 6 different outcomes. We don't know which one's going to occur until we actually roll that dice. It's not like, we're not thinking about experiments here like in the hard sciences. We're not got our pipettes and everything. We're not doing any of that, right? This is as simple as things that have an uncertain outcome. Once we start talking about this as well, we're running this experiment over and over again. This experiment has an uncertain outcome. When we start talking about coming up with a probability that they occur, we're assuming that we're running the exact same experiment over and over. So when I roll a dice, I'm the same person. I'm just rolling it with the same motion every time. I'm not, trying to. Sometimes I'm closer to the table. Sometimes I'm high up off the table to make it easier for me to roll whatever number I want. Right. So we're running the exact same way every single time. So the experimental outcomes are going to be every possible outcome you could see. So if I'm rolling a dice, right, unless I'm playing Dungeons and Dragons, what are what are the 6 outcomes I can see? 1, 2, 3, 4, 5, or 6. Those are my experimental outcomes. When it's something as simple as rolling a dice, it's really easy to know what the experimental outcomes are ahead of time. Let's say I asked, here's an example for it. We'll see if anyone knows it. Did I bring up Rook in this class before? No? Does any of you know what Rook is? The card game? Yes? No? Okay, so Rook is like pretty euchre. It's kind of like a bigger game of euchre, right? There's more cards, there's like a Rook card, right? But if you've never played this game, you don't know what cards exist in this deck, right? So if I'd say, okay, you're going to draw a card at random, what's the probability you draw a Rook card? Well, you don't really know. You don't know how many Rook cards are in this deck. You don't know what are, you don't know how many of the other cards there are. And so you might start drawing out a card, record it, put it back in, shuffle, draw another card, write that card down. And over time, right, if you draw enough cards, if you draw one card enough times, you'll have drawn every single card eventually, right? And you'll realize what the different outcomes are that you could see, right? But sometimes it's easy. Like rolling a dice, we know ahead of time. But other times we actually have to run this experiment to realize what these experimental outcomes are. Now, if we run enough of these experiments, eventually we'll be able to understand every single outcome that exists. Right? But if I've never seen, if I have a 6-sided dice, but you don't know what the numbers are on it, right? Well, then you'd actually have to roll it a couple times to realize, okay, this isn't a 1 through 6 die. Maybe this is, it's got 11 through 15. Well, I don't know that until I roll it, right? And then I record what the number that came up. So if I only roll it 3 times, right, I'm only going to see 3 of, at most, I'll see 3 of the possible 6 outcomes. Right? So if I don't run this experiment a lot, my sample space, the outcomes that I actually see, could be much smaller than the number of possible outcomes that are out there. Right? So I roll this dice 3 times. I'm not able to see all 6 outcomes. So my sample space are whatever 3 values I saw come up when I rolled this dice. So my sample space, as I run the experiment more and more, becomes larger and larger. And eventually, my sample space would match all the possible experimental outcomes. If I roll this dice 300 times, I'm definitely going to see all 6 of the possible outcomes. So we've got our experimental outcomes. We've seen the outcomes that we've realized by running the experiment. That's just in our sample space, right? Our sample is just how many times we've run this experiment and the outcomes that we saw. And then we have an event, which might be, look, I've got this 6-sided dice, but I'm only interested, right, in what's the probability that when I roll it, that I see a 3. So that event, seeing a 3 is what I'm interested in. So some, usually we'll define this, right? It'll be something kind of with the context of what our event is, depends on the example. But our event is going to be some subset of outcomes that's in our sample space. So if we had like a visual of this, right? Our experimental outcomes is everything we can see. Our sample space is just the outcomes that we realized by running this experiment. And then the event is some subset that we're interested in, right? We're not interested in every outcome, just a couple of them. This will become a little bit more clear when we start working through some problems, but this is the general setup of what we're doing. Okay. So, we're thinking about some examples that are really easy. If I flip a coin, my experimental outcomes there are just seeing the normal quarter. If I flip a coin, it can come up heads or tails, right? So I've got 2 experimental outcomes. I roll a die, 1 through 6, right? If it's kind of normal. Pull a card from a deck, if this is a normal card deck, excuse me, ace through king. Let's think about it. I think I have here, I was thinking more of a playoff football game, so I want to just see win or lose. If I have a soccer game, it's more like I see win, lose, or tie, right? So we can have really simple examples be our experiment, and the experimental outcomes are just any outcome that we can see, right? What are all the potential outcomes we can see? Let me try to think of another one. So let's say, we're thinking about all these experimental outcomes. They all have a probability associated. So if I'm going out there and I'm, maybe I go out around the university and ask people, how tall are you? And I start recording their height. Right? So I ask a person, that's my experiment, just a random person, write down their height. Ask another random person, write down their height. Eventually, I'm going to start seeing every single potential value for height. Right? But I know some of those are more likely than others, right? When I ask someone the probability they tell me 5'8", right? What would that be? 68 inches, right? That's a lot more likely than if I say, well, what's the probability of seeing the outcome be 7'2", right? I know that different values, right? In all these examples, especially the first 3, all the outcomes are equally as likely, right? It's equally as likely I see a 1, a 2, a 3, a 4, a 5, a 6, right? When I'm rolling a dice. When I'm asking someone how tall I am, I know that different values have different probabilities associated with them, okay? So this is eventually going to be the types of examples we get to, right? These ones where the probabilities are the same aren't as interesting, but they give us a place to start. Any questions on anything that shouldn't be too tough, just kind of setting things up here. So some of the notation of how we're going to write this, we're interested in the probability of these different outcomes. Oops, there we go. The way I write these probability of some event, right? So if I was interested in the probability that when I asked someone if they were 7'2", that's the event I'm interested in, I would write that P and then in parentheses, whatever that event is. So my event there was that height is equal to, what would it be? 72, 84, 86 inches. Right? It would be 72 if I'm doing math now. Right? So this probability of any event we're interested in, for now we can just think of the event being one outcome. We'll eventually get to some examples where the event could be, well, I'm rolling a dice, so it's the probability I see a 2 or a 3, or a 3 or a 4. Right? But for now, we can just think about an event as just one outcome. Right, so what's the probability to roll that dice? I see a 3. So the probability of the event, P in parentheses E, that's how I call that. What's the lowest that probability could be? If I'm rolling a regular 6-sided dice with 1 through 6, what's the probability that I roll a 10? 0, right? It can't happen. It's not one of the numbers. So the lowest we can see this probability would be is 0. What's the highest probability we can see? Very unlikely kind of scenario, but the highest, if I told you, what's the probability that if I'm rolling a double-sided, or sorry, if I'm flipping a double-sided coin, right? There's heads on both sides. What's the probability if I flip it, I see heads come up? It's guaranteed 100% or a probability of 1, right? So we know that this probability of any event has to be somewhere between 0 and 1. And we started out thinking about that issue with the connect, right? This probability in probability format, all we're ever going to see is something between 0 and 1. Because it's really representing like the proportion of the total outcomes that could be this event, right? It's 1 of 50 outcomes. It's 1 of 10 outcomes, right? Any questions on this? The other thing that we have, and this is where our probabilities, we kind of already introduced this idea when we were looking at relative frequencies. Remember, the relative frequencies always had to be between 0 and 1 because, we're looking at our data set. At most, this outcome is all of the observations, which was a total of 1. But when we had different outcomes for a variable, right, this was the idea that we could see, I don't even know what was the example we used. It wasn't car colors, but you can think of, I know at one point I used the example of what's the probability I see 0 kids in a household, 1 kid, 2 kids, 3 kids. But, if we took every possible outcome for that variable, we said those relative frequencies should always add up to 1, right? So if we took the relative frequency of every single possible outcome for a variable, they should add up to 1. Same kind of idea here. If we take every single outcome and we add the probabilities up of every single outcome, right? Well, that should represent all of the possible outcomes we can see. That should represent the space of 1. Okay. So just like our relative frequencies, our probabilities for every outcome should add up to 1. This will help us when we get to something. So how we're going to assign these probabilities, and this isn't, I won't get too in depth. I won't waste too much time on this, but there's going to be 3 different ways. So we've got the classical method, empirical method, and the subjective. So we'll go over each one of them a little bit individually here now. So the classical method of assigning probabilities is basically in scenarios where every outcome is equally as likely. So if I'm rolling a 6-sided dice, what's the probability I see a 1? Intuitively, it's just going to be 1 over 6, right? Probability that you see 2, 1 over 6. Everything is equally as likely. What if you flip a coin? Probability you get a heads, a regular coin would be what? Yeah, 1/2. So what are you doing here in both scenarios? If every outcome is equally as likely, what you're really saying is the probability of any one outcome, I'll get out of the way in a second, is 1 over n. 1 over the total number of outcomes you could see. If there's 100 different possible outcomes, each outcome would be equally as likely. It would just be 1 over 100. So this is kind of actually what we've been doing up to this point when we're thinking about finding means and things. Remember, we're weighting each one by 1 over n. Each outcome is 1 out of the total number of possible outcomes we could see. So this makes sense in a lot of examples, like flipping a coin, rolling a dice. Excuse me, I'm thinking about flipping a coin twice in a row. What are all the possible outcomes I could see? I could see heads and heads and tails, so on and so forth. I have 4 different possible combinations. So what's the probability if I flip a coin twice in a row that I see it come up tails twice? It would just be, well, that I see tails come up twice, right? There's only 4 different possible combinations if order matters, right? So the probability I see tails come up twice would just be 1 over 4, right? 4 possible outcomes. Probably about any combination there could be 1 over 4. So that one's probably the easiest one. So are there any questions on that before we can move to the next couple? So the next one is probably what we do more in practice. This one, like I said, this only fits kind of like gamey scenarios. But I'm thinking about, well, okay, if I go up and ask someone at random, what's the probability that they own a pet, right? Well, I know that it's not 50-50 pet ownership in the general population. I can't just start assigning equal probabilities to owning a pet and not owning a pet. So a lot of the times we're going to use this empirical method, which is to look at a bunch of old data, look at this experiment that's been run in the past, from the previous outcomes, determine what probabilities of that outcome will be in the future. So maybe I'm thinking about someone's favorite cuisine, right? I've got different classifications of what their favorite food is, but I don't know what the breakdown looks like amongst all state students, right? And so maybe I go out and ask 60 students, record their response, and 15 of them chose Mexican food. So what I would do is say, well, okay, look, based off the data I have, based off this survey question I've been asking people in the past, I know the probability that if I go ask another student at random, that they'll respond with Mexican food based on the data I have would be 15 out of 60, or about 1/4, right? 0.25 or 25%. So I'm using kind of old data, and most often this is going to be, we're looking at like survey data or responses from the general population. Like we don't have, we don't know what every single person is going to respond to our question with, but if we have a bunch of responses from that population, right, we have our sample, we can generate probabilities from that. And that's really how we do that. That's basically what we did with relative frequencies. We would go back, look at this variable that we've collected all this data on, and then say, okay, how many of the total number of responses were this specific thing? So how many of the total households we have responded with they have 0 kids, right? And that's the probability if I ask someone at random that they have 0 kids in their household. But I'm getting that probability, basically that relative frequency, from some existing data. So this is more often than not going to be how you assign probabilities, unless you have one of these unique kind of examples where everything's equally likely. Any questions on that? And then the last one, which kind of seems hokey, is the subjective method, right? So based off of some knowledge or expertise, you just assign the probabilities. Well, this seems kind of hokey, right? But you can imagine a scenario like if we're thinking about a company's trying to hire a CEO, and I've got 4 different candidates. Well, I can't use the experimental method here because I can't run this hiring process over and over to determine, okay, how many times does this company choose candidate Hill and how many times does it choose candidate ranking, right? Like that, you can only run this one time. So I have no data to look at, right? In terms of, I haven't seen this experiment being run before. To say they're all equally as likely is kind of ignorant, right? Potentially Andy over here is fresh out of high school and did this as a joke, right? And he's only ever worked at, I don't know, Taco Bell, not to hard from that, but he doesn't really have an experience running a company. So you would know his probability of getting this job are probably next to nothing, right? Almost 0. Right? So to simply assign equal probabilities with the classical method doesn't seem to make sense. So what would we do? Maybe find someone who's in this industry, look at kind of the resumes and the track record of each one of these individuals, and then say, well, look, all these are 3 failed CEOs. This, ranking here is, has had 3 successful businesses. He just had a location change, and so he's just looking for something new, right? So we might, know that one of these candidates is way more likely to get this job than the others, right? Based off of their track record. So it does make sense sometimes, but for the most, most part, we're going to be using that empirical method for a lot of the different examples we'll look at. So, with the subjective method, welcome to probability statistics, where everything's made up and the numbers don't matter, right? So you don't know what show this is. Should all go. Someone knows what it says, probably. It's been like a reboot, right? Yeah, whose line is it? You should all go back and watch some of the old ones. The old ones are way better, right? They got away with a lot more stuff. So, we'll now start thinking about how we actually look at these probabilities, some different things we can do with them. So I will go through and give you kind of a toy example. We'll kind of not be thinking so much about probabilities yet, and more about like the potential experimental outcomes. So let's say, let's see if this blue one shows us a little better. Let's say I've got event A, and the possible, we're thinking about rolling a dice here to make it kind of easy. So maybe I define this event A that I'm interested in is that a 3, a 4, or a 5 comes up when I roll this dice, right? So those are the 3 experimental outcomes that are in my event A. A complement is just going to be every outcome that's not an A. So when we use this superscript C, this is the kind of complement that's telling us that's every outcome not in event A. So here, what would those values be? So 2 and 6 and 1, right? 1, 2, and 6. I'm rolling a 6-sided dice, are the only outcomes I could see that are not in event A. Okay? So the complement is every outcome not in whatever event you kind of, use that superscript on. Here, A. I'll define event B as 1, 5, and 6. So what would B complement be? Yeah, just every outcome not in B, which would be 2, 3, 4. If you don't want to write these squiggly lines, you don't have to. I just kind of, that's how we kind of use set notation. All right, so we've got our complements. We also can think about the union of events, right? So A union B is just everything, I'll write underneath it, that's in A, and the way we typically say it in English, we can say A union B. Also, we say A or B, right? It's any outcome that's in either event A or in event B. So what are all the possible outcomes that are in either A or B here? So what? Not quite, right? So the ones that are in either A or B would be 1. Well, 2 is not in either one of them. 3 is in A. 4 is in A. 5 is in both of them. And then 6, right? So basically, it's all these outcomes that are in either A or B. Right? So 1, 3, 4, 5, 6. Any questions on that? And I think, yeah.
Is there anything that we write in A union B to show that a 5 is more probable than what's similar?
So up to this point, we're not thinking about the probability, right? So it's not that it changes the probability because you're just defining different events. So it's not that there's like 2 5s showing up. It's just that if I'm interested in event A, 5 is one of the outcomes I'm interested in. If I'm interested in event B, 5. So whatever probability is seeing 5, that hasn't changed. It's just that I'm now interested, right, in whatever event I'm looking at, that I see that outcome of 5. So, with that, you're thinking, all right, because the next thing we're going to do, so I'll get out of the way here, right, is the intersection of A and B, right, or A and B, right? So a good way to remember this, right? This is actually a set sign. It's not a U, but it looks like a U. So union, and then some people say, you've got the upside down U or that upside down set sign. You kind of think about if you did a line through that looks kind of an A, so A and B. However you want to remember that, that's just one that I've seen people say that makes sense. But really, what this is saying is, what are all the outcomes that are in A and in B? So here, what would the intersection of A and B be? The only outcome that's in both of them is 5, right? So here, the intersection kind of helps us identify that this outcome is in both these events. I can't really pick that up too much from the union. I just know that what outcomes are in either one of them, but the intersection tells me what outcomes are in both of them. Any questions on that? All right. So the next one, which is what that additional video will kind of help out a little bit more, and what we'll kind of start out and start talking about on Wednesday a little bit more about, are conditional probabilities. Okay. So for now, I'm going to give you an idea of what this means, but really it's a little bit easier to understand when we actually think about probabilities as opposed to just like the sets, right? And the kind of outcomes. So A with this like vertical line, and then B, whatever's on the right-hand side of that vertical line, basically what you're assuming that event has already occurred. So, I always kind of use the example of, if I'm thinking about event A, is that I walk outside the building and I slip and fall. Right? Hopefully I'm not that clumsy. The probability of A is relatively low. The probability today when I go to leave the building that I slip outside and fall is relatively low. However, if event B is that it's freezing rain, and I say, okay, if I'm thinking about what's the likelihood event A occurs now, that I slip and fall when I walk outside, given that I'm telling you it is freezing rain out, right? Well, now the probability of A has changed a lot. So you can imagine how kind of conditioning on something else gives you more information about how likely or unlikely certain outcomes are, right? So for now, kind of just knowing the notation is whatever's on the right-hand side of this vertical line, you're basically saying, okay, that has already occurred. I know that that has occurred. Now, what's the probability that I see that? But like I said, we'll dive a little bit more into this conditional probability, conditional idea when we're dealing with actual probabilities, but just kind of getting the notation out of the way for right now. So, if we want some nice visuals of some of these things, we'll start using Venn diagrams. So here, kind of each circle represents an event, right? Circle A is event A. Circle B are all the outcomes that are in event B. Right? So we have to think about these Venn diagrams represent all the outcomes possible, and then the outcomes that are in this blue circle, those are the outcomes that are in event A. The outcomes that are in the part B over here, the blue circle, well, those are all the outcomes in event B. The entire rectangle here represents, these are all the possible outcomes. So if I'm thinking about the area of that rectangle, I want to connect that visual to what we'll actually be doing mathematically. That entire rectangle represents every possible outcome. So if I add the probability up of every possible outcome, that space should have an area of 1. If I add the probability up of every single outcome, it should add up to 100%, which in probability format is 1. So that rectangle area is 1. And then you can think about, well, maybe the probability of A occurring is 0.25. Well, then you would think about that circle A, that area represents 0.25 out of the total area of 1. Right? So that's how we're kind of connecting these probabilities to these Venn diagram visuals. If I then want, what are the outcomes that are in event A and B, right? The intersection here. Well, that's just where they overlap. Those are the outcomes that are in event B, but they're also in event A, or they're in both circles, right? That's the area or the space that's in both circles, representing the outcomes that are in both events. If I wanted A union B, right, or A or B, well, that's just everything that's in circle B, everything that's in circle A, and we don't care if it's just in circle A or just in circle B, or if it's in both, right? It's every outcome that's in it, at least one of those circles. Okay? So these are kind of some nice visuals of our intersection, our union, and then just the events themselves. Okay? Any questions on that? You guys seen these used before, probably at some point, Venn diagrams. Some of you have it. So we can also put these into what we call a contingency table, right, or a joint probability table. Okay. So we might have two events. Let's think about these as event A and event B. Well, each event would have its own complement as well, right? A complement, B complement. So the way that we're going to set this up is we have these top 4 left cells, which all represent intersections, right? So these top 4 left cells represent the intersections of whatever the row and column headings are. So, this 0.4 represents the probability of A and B. Probability I see an outcome that's in event A and B is 0.4. The totals represent the probability of the row or column heading you're in. So here, the probability of B, we'll go down to the total is 0.5. Probability of A complement, we'll go over to the total is 0.4. So those totals represent the probabilities of the outcomes themselves, whatever the row and column heading is. The top 4 left cells represent the intersections of whatever their row and column heading is. Now, if I think about a couple of things going on in this table, the first one I'll kind of set up is, I'm jumping the gun here, but I think it's a good point to do it. If I've got event A, where would its complement be? Which is every outcome that's not in A, right? So every outcome not in A would just be this area out here, right? So if I take event A and I add to it its complement, what should that add up to? The probability of those 2 events. It's the entire space, so 1, right? So notice, look at these total columns. The probability of A plus the probability of A complement, 0.6 plus 0.4 is 1. And if I look at probability of B plus its complement, 0.5 plus 0.5 also adds up to 1, right? And that's just this idea. I think the visual here makes that a lot easier, right? If I just look at this circle A, everything outside the circle would be basically fill up the entire external outcome space. So those two things have to add up to 1. But we'll use this a little bit later, but the idea would be if I add up any event, the probability of any event in its complement, I should get the value of 1. I can also think about these totals. I can actually reproduce them by adding across the rows or down the column. So if I just gave you the top 4 left cells here, you could come up with the totals by adding across the rows or down the column. And I'll show you why in a second, just so you don't have to believe me. But 0.4 plus 0.2 gives you that 0.6. 0.1 plus 0.3 gives you that 0.4. 0.2 plus 0.3 gives you 0.5. But I can add down the columns and across the rows to produce those total values. So why can I do that? I'm going to show you all. Right? It shouldn't be maybe quite 100% clear to everyone why yet. So I think what I want to do. Let's say this is circle A. And here's circle B. Here is B complement, okay? All right, I just blue shaded area, right? Everything that's not in B, that's B complement. Right, so if you're not doing this in colors, it might be a little bit more difficult to kind of reproduce this, but maybe your vertical lines here represent B complement. So if I think about, all right, if I'm just interested in the probability of A here, notice, I'll try to draw it right. If I'm in event A and I'm in event B complement, that would be right, here's this red area representing A, where the red and blue area, or the vertical and horizontal lines overlap, that's all the outcomes that are in circle A, but not in B. Right? So that kind of overlap represents the probability of being in A and outside of circle B. So we're not in B, we're B complement. So that area where they overlap, the vertical, horizontal, or the red and blue lines, is all outcomes that are in A and in B complement, right? We're not in B. This kind of area right here, we already said that represents what? So all these outcomes would represent the probability of what? Being in A. These outcomes, with 2 circles overlap, that represents the intersection, where all the outcomes that are in A and in B, right? This upside down view represents the and. Any questions on that? And so these outcomes are in circle A and they're in B. There's that kind of red shaded area. All the outcomes are where these red and blue lines overlap. Well, those were in circle A, but not in circle B. So we can break up A into these 2 components, right? I think of it this way. If I'm interested in what's the probability when I walk outside and I slip and fall, well, the probability that I slip and fall and it's freezing rain outside, plus the probability I slip and fall, sorry, I should say A and B would be the probability I slip and fall and it's raining outside, plus the probability I slip and fall and it's not freezing rain outside, which is every possible outcome, right? So those should just add up to 1, right? Because I've defined it as simply not freezing rain. Any other weather outcome will be kind of contained in this group. So those 2 probabilities should always add up to 1, which notice probability of A and B plus the probability of A and B complement, right? That's why I can add across the rows, and that just reproduces the probability of A itself, right? That total. Like I said, we don't have color, that's why I'm kind of using these vertical and horizontal lines here. But any questions on this? This is a little bit, this is tricky. But it kind of supports why it works to add across the rows or down the columns to produce these total values. Okay? So if I wanted the probability of B, what would that be here? Just the probability of B. So what do these total columns represent? Probability of the either column or row heading. So I wanted the probability to be 0.5. I just go down that total value. Okay. Same kind of idea where it's there. I didn't have that total value. I could just add up the probability of A and B and the probability of A complement B. Or add down the columns. I kind of mentioned where I could find this. What if I wanted the probability of A and B? What value would that be? So the probability of A and B. Yeah, right. Where do I find the intersection values? Those are just the top 4 left cells, right? These top 4 left cells here, that says all represent intersections. And they represent the intersections of whatever the row and column heading is. So if I want the probability of A and B, that's just going to be 0.4. What if I want the probability of A complement and B complement? That value should be 0.3, right? I go to A complement and B complement, 0.3. So that's how I read this. Okay? So hopefully, paying a lick of attention to what I just said, this should be a very, very simple question and shouldn't take us more than 30 seconds. So what if I want from this table, right, the probability of R1 and C1? Okay? I want the probability of R1 and C1. I'll give you a little bit of time to get your eye clickers out, get ready, get into the thing, and probably here 30, 45 seconds we'll go over. Gives me a chance to drink the water. All right. Everybody got an answer in? Anybody need a little bit more time? We're good? Okay, I'm gonna close it out. All right, so what should the answer be here? What's the probability of R1 and C1 is? A, right? Oops, maybe, there we go, 0.4, right? I'm just going to where those two events intersect here in the table, the top 4 left cells telling me the intersections. So 0.4 represents the intersection of R1 and C1, or the probability of seeing R1 and C1 intersection. It's not too bad. Just to kind of go through a couple things here before we're done today. Some of the laws we'll start talking through. Next class, we'll really start using these probability laws. But for now, if I'm looking at unions or intersections, it doesn't matter which way I write it. Saying what's the probability of A and B. So maybe what's the probability that someone makes, $50,000 or more and is, I don't know, older than 45 is the same thing as saying what's the probability that someone's older than 45 and makes more than 50,000. It doesn't matter the order in which I say, right? So that'll help us out down there. And I always just like this one. When you say it's fine, actually fine, right? We're thinking about intersections here. That intersection is relatively small. Right? So that's when you can start thinking about these Venn diagrams representing our intersection. We introduced this a little bit earlier. Did I erase it? Yeah. So that was when I had the probability of A plus the probability of A complement. We said those areas always add up to 1. If I rearrange that a little bit, I can get this equation where the probability of the complement will always just be 1 minus the probability of the event itself. Right? So just taking the idea that if I took space A here, probability of A added to the space of A complement, probability of A complement was always add up to 1. Rearrange that equation a little bit, and if I know one of them, I can always find the other. If the probability of A is 0.2, I know the probability of the complement is 0.8, right? Whatever would get me back up to 1. That's pretty easy. I think I'll cover this and we'll kind of call it today. So one thing that's we can use the contingency table to do this, but I think the visual here kind of helps. So if I wanted the union of A and B, right? So what outcomes are in A or in B? Let's everything in circle A and everything in circle B, right? It can be in either one of them. I shouldn't have used the word and there, but it's in either one of them, right? It could be in circle A, in B, or in both. So if I simply took the probability of A, so this circle A, and I added to it the probability of B, that area of circle B, I'd be double counting whatever's in the middle, right? Right, so if I added this area to this area, I've counted what's in both of them twice, right? Well, if I know that I've counted it twice, if I just subtract it out once, I know I've only counted it one time, right? So by adding up the probabilities and then subtracting out their intersection, I've ensured that I'm only counting every area in either circle once. So that's kind of the intuition behind why this equation works. If I want the union of two events, I can take the probability that I'm in event A plus the probability I'm in event B, and then that would have double counted the intersection, so I subtract that out once, and now I've roughly, the probability that I'm in either one of them, right? I've only counted every one outcome once. Any questions on this? So you maybe can imagine, how could I use a contingency table to find what that union is? Well, I can look up the probability of A, and look up the probability of B, and I can look up the probability of the intersection. So I'm going to skip ahead here a little bit. Right. We're using those values we were using before. If I want the intersection of A, if I want the union of A and B, I said that should just be the probability of each event minus the probability of the intersection. So the probability of A is 0.6, the probability of B is 0.5, the probability of the intersection is 0.4. Well, I've now got everything I need, plug those values in, and I can figure out what the union is. So what we'll start with next class is there's actually another way we can find the union. I'll kind of break it down for you, but then we'll start jumping into some different things. Eventually, we'll kind of get these conditional probabilities, and that's what that video is kind of covering. Some interesting contingency table examples. Other than that, I will be in my office today, like 2:30 to 3:30. The door is shut, not giving last minute questions on Excel. Otherwise, I will see you guys on Wednesday.